Okay, Garth, take it away. Everyone else, please mute your microphones.
Hi, good afternoon, everyone, and thanks very much for that a very nice introduction. So my topic this afternoon is going to be ADAS EMC testing and antenna measurement. And during the course of the presentation, I'll talk through some of the sort of feedback and changes we've seen in the automotive industry, mainly through our interactions with customers and other people involved in EMC testing or product design or even in the marketing field. I'll then talk a little bit about the current status of some of the more popular standards that are used by automotive manufacturers and component manufacturers, and then take a little bit of a sidestep into some of the new tests that we see being, introduced and developed by companies like ourselves to support testing within the industry. And ADAS and ADS testing is another offshoot of some of these additional tests that we see people getting involved with as it relates to the ongoing development of vehicles. And then hopefully we'll have a very vibrant question and answer. So I'm looking forward to a lot of exchanges and feedback from people that are involved in testing that, possibly have some experience with some of the topics that I'll be discussing. So just by way of introduction, I'm sure most of you are familiar with RF chambers and EMC testing, but I like to make sure that we have a common understanding of some of the important aspects of chamber design and why some chambers are used for a particular type of test and not for others. And I think it's fair to say that RF chambers, by and large, are used to provide a controlled environment. And the controlled environment that we're concerned with is often related to performing one or other type of RF type of measurement. In our case, obviously, it's related to EMC or electromagnetic compatibility testing. Now, in terms of the design and use of the chamber, the level of control that's required and designed into the chamber really depends on the type of test that's going to be performed in that environment. In most cases that we're concerned with, it's EMC testing. In some cases, it involves antenna pattern or some type of over-the-air communication tests, where you want to make sure that the environment within which you're testing a particular device is free from outside interference or is not able to interfere with other things that are happening outside of the measurement environment. So that defines the level of shielding that's required in one aspect, but it also defines the level of reflections that can be tolerated within the test environment. Frequency of operation becomes an important aspect when you look at how the chamber itself behaves at different frequencies. And in some cases where RF absorber lining is used, the performance of the RF absorber is very frequency dependent. So the frequency of operation would dictate the type or size of absorber that's used to line one or more surfaces of the chamber. And then on a sort of as a flip side to that, you have the level of internal reflections that can be tolerated. And what I mean by that is, in addition to an RF reflection-free environment, you can also have an environment where you want RF reflections, like in the use of reverberation chambers. And we'll touch on that in one of the later slides. So all I'm saying is here that there are a lot of different designs that are possible for performing measurements in an RF environment. And how the facility is designed really depends on the type of test that's being done. Now, one of the things that very many of us get involved with is supporting the development of standards and the maintenance of standards documents. And in the automotive community, there are a few different bodies. CISPRA and ISO are a couple of the bigger international bodies. There's also the SAE that has their own series of standards. And I sit on the US CISPRA 25 committee with several of my colleagues. And we are involved with the development and maintenance of CISPRA standards, the CISPRA 25 and CISPRA 12 and 36 standards specifically under the sort of auspices of the CISPRA D subcommittee. And there are sort of equivalent or parallel groups in just about every member country that serves the same function. All of these members are staffed by volunteers. They all work in industry in sort of one aspect or another, and come together to help support the formulation and development of these documents. Another one is the ISO group, and again, the TC 22 Subcommittee 32 is involved with the immunity standards, and this group covers the ISO 11451, 452, 7637 as the three main documents that cover full vehicle and component immunity testing. And why I bring this up is because how the standard develops is very directly related to how the industry as a whole develops and introduces new product and markets new product in the industry. So feedback from the industry and from manufacturers into the development of standards is a very important part in making sure that the facilities that are designed to support tests have input from a broad range of users within the industry. If we look at the standards specifically, I'll talk in a little more detail about the CISPA 25 and ISO documents, because those are the two main documents that cover the components and full vehicle immunity and emission tests. And there are a number of similarities and differences between the documents and the environments that they specify for performing those measurements. So if we look at CISPA 25, this covers component emissions measurements, and CISPA 12 covers full vehicle emission measurements. And there's a subtle difference between the two in that CISPA 25 looks at emissions that could affect the sort of receivers on board the vehicle, whereas CISPA 12 looks at emissions from the vehicle that could affect receivers that are not on the vehicle. So CISPA 12 is really geared to protecting the environment, the rest of the broadcast industry and the rest of the outside RF environment, whereas CISPA 25 is protecting the receivers that are on board the vehicle, making sure that there's reduced risk of sort of self-interference. CISPA 25 is also a little odd in that it has a section that deals with sort of components and subassemblies, and a section that deals with the measurement of emissions that are received by the vehicle. So there's a full vehicle component and a component of CISPA 25, which is a little different to some of the other documents. The ISO standard looks at immunity tests for passenger vehicles and commercial vehicles. And as with all of the standards that I'll mention, they cover vehicles irrespective of the sort of propulsion type. Traditionally, these would relate to combustion engine vehicles, but it also covers the hybrids and the electric vehicles as well. So CISPA, the ISO 11451 document covers full vehicle immunity, and the ISO 11452 covers component immunity, and the -2 is just one of a series of subsets of the standard. This one relates to tests in a absorber line facility. Now, one of the things I always try to mention when talking about standards is the limitations of what standards are expected to provide. A lot of people buy products and, it says that this product is designed to do such and such. Therefore, it must be tested to prove that it does that with some degree of proficiency and satisfaction. When it comes to a lot of these EMC standards, the intent is to provide a level of resilience to the RF environment, the electromagnetic environment, but there are no guarantees. If a product is tested to a standard and meets the requirement of the standard, it does not guarantee that that product will not create interference, and it will not guarantee that that product is free from being interfered with other RF sources in that environment. So that's a very important point to make about what standards can and can't do. Standards are really designed to provide a standardized method of doing tests with guidance on how the test can best be performed. And in some cases, it gives guidance on, acceptability limits that give you a good pass-fail criteria in deciding whether a product meets or does not meet the requirement of a standard. But it's important to understand these limitations of what that document is intended to do and how it is intended to be used. In a lot of cases, there are ambiguities in the wording or the interpretation of what's written in a standard document. And it really comes down, in a lot of cases, to common sense and understanding what the intent of the document is in how you interpret what the document says and how you act on what's written in the document. And this is where we get a lot of input from the industry, where a document's been published, it goes out in the industry, the test labs and the users use the standard. There's some ambiguity or some uncertainty or some recommended improvement in a particular practice. That could be fed back into the local standards community. And if there's general and broad agreement, it could be part of a revised version of that document. So this is how these things evolve. Manufacturers come up with a new widget, a better way of doing something. They come up with an improved method of testing this new widget. Again, that gets fed back to the community and introduced potentially into a new version of the document. And what I'm trying to get to here is there's a mechanism for this feedback to arrive at the standards community. And quite often it lags what happens in the industry. So right now, I mean, there are vehicles that are on the road with features that are not necessarily covered in the strict description of existing standards. And that's just because of the sort of gestation period of a new document or a revision of an existing document. It takes time to get agreement and to do whatever validation tests and wrong rubbing measurements are necessary before these things get fed into a standard. And quite often, it happens sort of years after a particular feature ends up in a product. And that's not unique to the automotive community. It happens in a lot of other industries as well. So just a very general sort of topic that applies to standards in general, making sure you understand the limitations of what the document does and the intent of these specific standards. Now, in addition to the sort of industry standards, the international documents under CISPA and ISO, there are also manufacturers' own documents. All of the OEMs have their own EMC standards, as they've got their own other standards as well. And in a lot of cases, these standards are far more onerous, far more severe, have far more rigorous limits than the international documents. And sometimes test labs get exposed to the use of these documents and are in some cases required to test these documents. I hope you can't all hear the screaming in the background. I assure you nobody's been murdered. And then you have obviously the international standards, which is often used for industry acceptance and in some cases regulatory compliance. In the European community, for instance, the ECE Reg 10 document is a barrier to trade document, which means that a manufacturer must meet the requirements of this standard before they are legally allowed to sell a product that's covered under that standard in the European community. So that's what I mean by a barrier to trade. In a lot of other countries, it's a good industry practice, and in some cases there are legal ramifications if there is a non-compliance. But in a lot of countries, you can still sell a product even if, strictly speaking, it doesn't meet the requirements of a standard. Although in some cases you may not be allowed to do that legally. But from a barrier to trade perspective, in Europe, you're just not allowed to sell products unless they've got that EC mark associated with the regulation 10.6 for automotive components and vehicles. I mentioned that the standards are quite often broken up into individual sections, and I'll touch on some of those in a couple of the later slides. CISPA 36 is one of the newer documents. It was published within the last couple of years, and this one's specific to electric and hybrid vehicles because it's concerned with the low frequency magnetic emissions from the drive components of electric vehicles. It's also aiming at protecting emissions that affect off-board receivers. The range of tests is only up to 30 megahertz, uses magnetic loops at a 3-meter test distance, although the protection distance is out to about 10 meters. The test in an anechoic chamber is actually done at 3 meters. And within the standards community, there's work being done on the amendment or the next revision of this document at the moment. I touched on CISPA 25 and the fact that this one is geared towards protecting the onboard receivers. Frequency range, 150 to 2.5 gigs, extended up to 5.9 gigahertz. Currently at the 5th edition. And at the last meeting, there was a discussion about possibly breaking this document up into smaller pieces, just mainly to make it more manageable, because it is becoming quite a large and an involved document. With every revision, as we have, more and more amendments being suggested and introduced into the document. So there's a chance that the 6th edition of this document might see some fairly significant changes in the structure of the standard. This is a little overview of the main documents. The ISO standard, as I mentioned, is associated with full vehicle immunity. The one in the last one in the number is the giveaway. The 452 is associated with electronic or electrical subassemblies and component immunity measurements. In both cases, the recommended environment is enclosure, or shielded enclosure with absorber lining to limit or reduce reflections within that environment. On the other side, where we have emission standards, we've got CISPA 12 associated with full vehicle emissions, again performed in a absorber line shielded enclosure or on an open air test site or OATS. CISPA 25, as I mentioned, for full vehicle self-immunity emissions or component emissions. And then CISPA 36, full vehicle low frequency emissions. And then the overriding standard for the European Community, ECE Reg 10. And this document references a lot of these other standards as part in the body of the standard. So it's not just a single standard covering everything. It copies or references the procedures that are described in a lot of these other documents. Now, in meeting the requirements of this standard, as I mentioned, chambers are designed for particular applications and optimized for a particular series of measurements. And they come in all shapes and sizes. I've just shown a couple of examples here. The traditional EMC chamber, which is by and large either rectangular or square in structure, with a very well-defined sort of direct illumination path. You have your transmit or receive antenna positioned directly aligned with the device under test, or the area or volume within that sits. For the component test, you have a similar setup, the transmit or receive antenna directly aligned with the device under test. So you measure direct coupling or you transmit using this direct coupling within the beam width of the antenna. For different types of measurements, for antenna pattern measurements, for instance, something like a tapered chamber is very useful for a very broad frequency range when you're doing antenna pattern measurements. And this type of environment, very different absorber type and absorber treatment, different operating frequency range, but again, optimized for this type of test. And one of the things we've started sort of seeing being, I suppose, done more often than was done previously, is a sort of combination of facilities where you have chambers being built to support the traditional EMC testing in a rectangular type of environment, but also sort of fused with other structures, so that in this example, it can be used to perform antenna type measurements as well, using this long tapered or semi-tapered range. So again, depending on the type of measurement, the range of tests, the chamber can be designed and optimized to try and meet as best as possible the overall needs of the required body. I think across the industry, the design and operation of EMC chambers is very well understood. Just about anybody can build a shielded room with any sort of shielding material, from thick foils all the way up to thin sheets of metal with supporting structure. There are all sorts of RF absorbing materials that are available, and there are all sorts of techniques that are available for trying modeling and predicting the performance of these facilities. This is just one example here based on a ray tracing technique, where if you have information on the propagation characteristics of your measurement or transmit or receive antenna, you understand the volume within which you are interested in seeing what sort of reflections you're receiving, and you have information on the reflection and absorption characteristics of your absorber lining, then you can use a basic ray tracing type approach and calculate based on the energy in each ray that is incident on the absorber surface that arrives within your quiet zone. You can calculate based on the gain in this direction, the absorption at this angle of incidence and reflection. I know how much energy is going to arrive at my quiet zone, and I can see how that interferes with the direct path and calculate what sort of variation or ripple I will have within that quiet zone. And this is basically one of the techniques we use in a number of different chamber designs to predict what the NSA performance or VSWR performance is going to be for a particular chamber treatment. And what this allows you to do is optimize the layout of absorbers that you have on the surface. So if you know that with a particular range of or particular position of antenna and quiet zone, most of the energy will arrive in your quiet zone as a result of a single reflection at sort of the half angle of this path, then it means that, yes, you're going to need more absorber or better performance in this area, but you can probably get away with worse or less absorption in some other area, because for energy to arrive at this area from this wall, it must interact with other surfaces. So you have the benefit of multiple reflections or multiple absorption events before it arrives here. And, it just allows you to optimize the layout of the absorbers. So these are very well understood, and, a lot of lessons have been learned over the years on how best to treat a lot of these facilities to create an optimized environment. The standard gives guidance on the suitability of the measurement environments, and the degree of the guidance varies by standards. Some of the commercial standards go into very great detail with very detailed procedures for quantifying the uncertainty within your test volume. This is an example from CISPR 16, which is a standard that's used on commercial electronics or consumer electronic products. And what this does is defines a method of measuring the S21. You have an antenna on a transmit mast, and multiple positions of the antenna around the quiet zone within which the volume would sit. You perform this series of S21 measurements as a function of frequency and as a function of antenna scan height. And you compare the measured S21 with theoretical sort of free space environment S21 measurement to show how this compares to a free space environment. And it gives you a direct measure of the sort of quality of the chamber and an expectation of your uncertainty of measurements within that test volume. Now, I put this little note at the side here with reference to CISPR 12, because in the current version of CISPR 12, there is no chamber validation method. And there is an attempt, or there's work being done to come up with an acceptable procedure that can be introduced in the next revision of the document or another revision of the document. But what we found is that most manufacturers that are interested in testing large objects or objects at test distances that require chambers that would be used for consumer electronics would also benefit from using the same chamber for other tests as well. So in a lot of cases, we would actually use the same CISPR 16 validation techniques for manufacturers that are testing to CISPR 12, although it's not required in CISPR 12 to have that level of chamber validation. There's no harm in doing it. You end up with a chamber with performance that you can quantify, and it's good when you're doing your sort of combined uncertainties to know how much of that uncertainty is contributed by the chamber itself. This is just an example of the type of results that you'd get from an NSA measurement, a normalized site attenuation measurement. The CISPR 16 standard requires that the variation be less than plus minus 4 dBs. And in a lot of cases, it's quite easy to get much lower than those limits. But as with everything else, better performance means better products or larger absorbers, which often drives costs, in some cases, larger chambers. So it's often a balance between how good is good enough and how much am I paying to be as good as I need to be, and is it worth paying extra to be better? So all of these decisions have to be made by manufacturers when trying to decide on what product is required. And some standards do a better job of making that choice easier. In this case, you have a plus minus 4 dB limit, and you know that if the chamber meets plus minus 4 dBs, it meets the requirement of the standard. If it doesn't, then you may not have a compliant test facility performing those measurements. In some cases, it's not as clear cut when you look at some of the other standard documents. On the immunity side, there's a similar series of tests that are available in the sort of consumer electronics environment. The upper area here shows what's described in the IEC 61000-4-3 document, which covers the test sites used for commercial products. And this uses a 16 sample point method of quantifying the E-field uniformity in an area that corresponds to the position where you place your device under test when doing an immunity measurement. And the standard requires that the E-field vary by less than 6 dBs among all 16 of these measurement points as a function of frequency. In the automotive industry, there's something a little similar. There's the 1 or 4 probe field uniformity validation method, where at the test distance of the measurement antenna from the reference position in the vehicle, you're required to show that the field varies by less than 6 dBs when you measure it over the 4 probe method. And then there's another method where you look at the probes side by side or 3 probes side by side, again, to make sure that you meet the uniformity requirements. So there is guidance within the ISO documents, the 451 document for full vehicle testing, on how to characterize the uniformity of the field in the area where the component or vehicle under test will be positioned. And of course, the open area test site, or OATS, I think was the original RF test environment, sort of from which everything sort of spawned. So everything is referenced back to an OATS or an OATS type environment. And this is sort of characterized by a free field, obstruction-free layout with a reflective ground plane, with good propagation characteristics, with no reflections from any external structures. The challenge with this environment, obviously, is the fact that in a lot of cases, it's exposed to the weather, and it requires a bit of real estate, which is free from external RF influences. There's a lot of RF in the environment, so finding somewhere to put a big greenfield OATS that's not subject to cell towers and televisions and radio and everything else is very, very challenging. So what most people end up with is some form of enclosed facility which meets the minimum requirements of the particular standards that they'd be testing towards. So for EMC testing, the main sort of facilities that are used fall under the ALSC, the absorber line facility, which has a reflective ground plane, a semi-anechoic chamber with a reflective ground plane, or a far or fully anechoic room where the floor is also covered with RF absorber. And they are all in one standard or another acceptable facilities for performing either emissions or immunity measurements. One of the newer additions to certainly the automotive full vehicle immunity measurements is the reverberation chamber. This test facility has been around for several decades. It's been a part of the MIL standard 461 for several revisions. It's been a part of the RTCA DO1 6-day standard for avionics and aviation-related components, again for several revisions. And I, at the last sort of couple of meetings, we've been sort of formulating a version of this document to cover full vehicle immunity measurements. And I think the intention is for that document to be published in the near term as a part of the ISO 11451 series covering full vehicle immunity measurements with tests performed in a reverb chamber. Across the industry, they've been used under different standards. This example on the left covers sort of handsets, cell phones, to a CTI and 3GPP communications related standard. These larger chambers, this one would certainly satisfy the ISO 11452-11 reverb test method for component immunity. And larger chambers would meet the MIL standard DO160, as well as the ISO 11451-5 new standard for vehicle testing. Again, just an example of the types of facility that can be used for performing these measurements. And one of the features that I think would be part of the new ISO document is the degree of flexibility that's being introduced in this document. It's not specific to a test done in any particular type of environment. It's going to have guidance on the use of quite a few of the techniques that's used in industry. Everything that ranges from the flexible fabric tent, the VERC, the vibrating chamber where you shake the walls of the facility to stir the molds, through the traditional rigid metallic box with rotating mechanical stirrers, including metallic box with moving structures, moving walls as the method of stirring the molds. A lot of different techniques that are introduced. And another degree of flexibility in the standard is the extension in operating frequency range. We all know that reverb chambers are really usable above a frequency where you have sort of overmolding of the cavity. What this new standard will do is provide guidance on how the resonant cavity of the reverb chamber can be used even at frequencies below where it's reverberant, below where you have adequate modes for stirring. And there's guidance on how you can excite the limited modes and create E-fields within that cavity. And a lot of discussion on what the trade-offs are with operating below that lowest usable frequency. So for instance, if you're exciting the cavity with, excuse me a second here, I'm not sure why my battery's running low. Plugged in, hold on 1 second. This could end very badly. Why am I not charging?
You haven't switched outlet by any chance?
No, I don't. I'm plugged in directly to the wall. That's the scary part. Excuse me for 1 second. That's
No problem.
I'm plugged into an outlet. It's not live. Let's try that one. Wow. Okay, panic averted. I thought I was being safe by plugging directly into the wall outlet. Guess that one's not working. Okay, so yes, as I was saying, one of the advantages is the extension at the bottom end of the frequency range. So, for instance, if you're driving this cavity with an E-field structure or a low frequency antenna, where you don't have enough modes for stirring, the document gives good guidance on what the implications are of the increased uncertainty with making measurements at those low frequencies. So I think it'll be very useful. We are hopeful that there's broad adoption of the standard, and we're looking for good feedback on how it's used, what are the benefits, the advantages, the disadvantages, and if there are any recommended improvements that people see that will improve the uncertainty of the measurements and broaden the acceptability of the document. I think that would be very, very useful in coming standards meetings. And now my slides refuse to work. There we go. So a couple of the main advantages of reverb chambers, and I think this is one of the things that's driving its acceptability, certainly in the automotive community, is the fact that the device under test is fully immersed in the RF environment. And this is very different to the ISO 11451 type of direct illumination method, where you're pointing the immunity antenna at the device, at the car, at the reference position. and trying to couple enough of that RF energy into potentially sensitive components. In a reverb chamber, it's a little different. The device on the test is completely immersed in that environment. The RF energy surrounds the entire vehicle. And by stirring the modes, you are moving the hotspots and the coupling energy around the potential vulnerabilities, on and in the vehicle under test. So it's potentially a very severe environment for immunity testing. There are some potential gotchas when doing tests in this type of environment. One of the obvious ones is with the speed at which you change the position of a particular hotspot relative to a particular component. And what that relates to is how you stir the modes, whether you rotate that tuner or shake the fabric tent continuously, or whether you have discrete positions of the reflecting structure that can hold a particular field pattern for some fixed duration of time. And obviously that has an impact in how the devices respond. If you've got a component that when exposed to a particular level of RF would only respond after some fixed duration or past the expiration of some fixed duration, then that introduces a dwell time to the measurement. And if you're testing in a reverb, it's a little more difficult to make sure that you manage those dwell times adequately in describing or defining how you stir the modes within the cavity. Another technique that's introduced in this document is what we call the high-speed stirring or fast stirring, where you have a stirring mechanism that stirs the modes very, very quickly. And if you think about what's happening, if you stir the modes very, very quickly, you're creating this sort of average field density within the volume of the cavity, which sort of normalizes or equalizes the field strength within that volume. But it does potentially introduce some modulation effects that could result in the failure of a component which would not otherwise fail under CW conditions. So there are some things that you have to pay attention to when doing measurements in a reverb. And you really have to understand what the reverb chamber is doing and understand how your devices are potentially responding to the RF environment when you do that type of measurement. One of the things I would say, and I think this lends or provides a little bit of confidence in the technique itself, is that when compared to the method that's used in the communications industry for testing handsets, small wireless devices, base stations, they are able to achieve levels of uncertainty that are of the order of fractions of a dB to a dB in terms of field uniformity or field homogeneity within that reverberant environment. In the EMC community, we've sort of grown accustomed to much higher levels of uncertainty. I talked about the NSA test with a plus minus 4 dB field normalized site attenuation limit for acceptability in the standard. I mean, that's an 8 dB spread. I also talked about the 0 to 6 dB that you have for the immunity test environment. That's a 6 dB spread. So we're used to these sort of large numbers when it comes to how accurate is our field or how accurate is what we're measuring. In the communication industry, they're used to much smaller numbers. Fractions of a dB is a big deal. So it is possible to achieve very high levels of accuracy in a reverb environment. The downside is it takes a long time to do that. You have to store those modes and take lots of samples to get the uncertainty down when doing that. So again, it's a trade-off between test time, test cost, and measurement uncertainty. And if you can offset uncertainty by over-testing, increasing the field levels that you test to, then in some cases, that's an acceptable compromise. So we talked about a little bit about the standards, some of the work that's being done on the standards. We got to one of the newer environments that's been introduced in the way of the reverb chambers for full vehicle testing. I talked about a couple of the advantages and disadvantages. The standard also gives good guidance on the design and layout of a typical reverb environment. This one I borrowed from the IEC 4-21 document. And it's very similar to what we have in the new ISO standard. There's a defined volume within which the device would sit. In this case, it's consumer electronics. It could be a vehicle. It could be anything. You have a method of driving or exciting the cavity, transmitting energy into that test volume. And then you have some mechanisms for stirring the modes within that environment. All fairly standard, all fairly well-defined in the different standards documents. And then, of course, you have limits. The standards will also give guidance on acceptability criteria. As I mentioned, we have sort of gotten used to very large numbers in the EMC environment. And in the reverb chamber, it's no different. In a lot of these existing standards, the acceptable levels vary from 4 dBs down to 3 dBs for the field uniformity. The DO16 relaxes that a little further, going all the way to 6 dBs at the low frequencies, and then down to 3 dBs once you get above about 400 megahertz. So again, all well-defined and covered within the document, gives guidance on how you go about characterizing or calibrating the test volume, gives you what those acceptability limits are, and then gives guidance on how you go about testing devices within that measurement environment. So there's a lot of useful information in the document aimed at really helping customers understand what happens if you're in a reverberant environment and you're trying to do measurements with an insufficient amount of stirring or an inefficient or ineffective method of stirring. So this is one example of a project that we did, several years ago. It must be about 10 years ago now, where a particular customer had a large chamber built for aircraft testing that included wireless and high-frequency RF measurements on these aircraft. And they wanted to also perform some low-frequency EMC tests. And in order to support the test, they wanted to use a strip line E-field generator. This structure sort of generates vertical E-fields between the radiating element and the floor of the chamber. And the plan was to position this over the aircraft being tested and radiate it at fairly low frequencies, down in the tens of kilohertz to tens of megahertz. And one of the things we did was looked at how this structure would behave in the existing chamber that was built for higher frequency antenna measurements. And unfortunately, because it was built for higher frequency measurements, the RF absorbers did not have sort of good absorption at the low frequencies, down in the tens and hundreds of megahertz, tens and hundreds of kilohertz and a few megahertz. So what happened is, as shown in this model, if you excite this cavity with these low frequencies, you get these resonant modes because the walls, of course, are very reflective. They're covered with absorber, but they're still very reflective because the absorption is very low from that material. So you get these resonant modes that create these hotspots within the cavity. And of course, there's nothing stirring the modes. It's just a large anechoic chamber. You get these hotspots that mean that as a function of frequency, where you have a hotspot and where you have a null moves as you change to test frequency. So you have a device that's fixed, you have a structure that's fixed, and you have a hotspot that's moving very slowly as a function of frequency. So you could be very easily over-testing or under-testing this device without even knowing, because obviously you don't know where the hotspots are from just looking at the device on the test. So that was one of the problems that this presented. The other one, which was a little more complicated, is the fact that you were trying to drive this device with several tens of kilowatts of RF power. And of course, what the amplifier sees as you sort of change frequency is a series of intervals of going through very high visual sort of peaks, which result in the amplifier folding back to protect itself from these very, trying to drive energy into this very high impedance and highly mismatched load. So that became another knock-on problem with trying to use this device for that type of measurement. So again, just to illustrate some of the complexities with trying to use a facility that may be adequate or ideal for one particular type of test, but not necessarily designed and suitable for a different type of measurement or measurements in a slightly different frequency range. So you always have to bear things like this in mind when trying to adapt facilities to do some of the more complex tests that we're talking about in the next couple of slides. And I touched on these chambers. These are the standard component level chambers that, again, we're all mainly familiar with for CISPA 25 and ISO 11452 type measurements. And as a coincidence, it's almost exactly the same facility that you'd use for DO16A and MIL standard 461 component testing. In fact, these chambers are sort of the grandchildren of the MIL standard traditional component test setup. Not very much has changed over the decades in the design of these facilities. And, you know, one of the downsides of the standards environment is the fact that you need consensus in agreeing the next revision of a document. And sometimes it's difficult to introduce something that's very new because you know, new techniques often drive new designs, and new designs drive cost. And there's always careful consideration given to how best these new techniques can be implemented. You know, always at a reasonable cost. So a lot of these designs have been around for several decades with you know, very little in the way of improvements over the generations. This is just an example of some of the parts that we have for the component immunity standard. As you can see, it covers a whole host of different environments. As I mentioned, that part 2 covers the absorber line shielded enclosure. And again, there are different environments, strip lines, traditionally housed in a shielded enclosure. There are strip lines that operate out in the open for some of the military standards. The -11 or part 11 covers component reverberation chamber testing. And then you have the transient and the conducted parts of the standard, and the TEM cells that covers GTEM cells as well. Again, also subparts within this component level test document. One of the additions to the CISPA 25 and ISO standards that was introduced with the introduction of hybrid and electric vehicles was guidance on a method of loading the device on the test. And this example, the device on the test is the electric motor, the drive motor for the vehicle, and the inverter that provides the power to drive the motor. So the typical test setup was used with the exposed cable harness, the power source for that device on the test, and then the load for the device on the test. Very similar setup. The only addition was this suggested method of loading the motor with an inverter or motor drive, motor dyno, and this dyno could be, you know, anything from a water break to a eddy current dyno to a AC or DC motor, anything that could be used to act as a load for the motor under test, and connected so that it maintains the RF integrity of the environment. Again, in essence, can be used for this type of setup. As with most things, it's not perfect. If you were starting to do this test from scratch, you would probably end up with something that looks a little different. But it is, as is often the case, an extension of something that already existed in the standards document. And it's often a lot easier to make incremental changes than to try and make these very big changes in a test method or a test technique. So this is one of the incremental changes that was introduced in edition 3 or 4, I think, of CISPA 25 to support hybrid and electric vehicle components. So I think I've talked enough about standards, and I wanted to run very quickly through the 451 for full vehicle testing. And again, not much has changed in terms of the standardized method of performing the test. The vehicle still sits on a rolling road or axle stands or surface mounted chassis dynos so that you can operate the drive components, whether it's a combustion engine or an electric motor. And the reason there is to try and create a representative environment of emissions during the course of an emission measurement, or the opposite during the course of an immunity measurement. And the part 5, it says under development, so it's in production basically for publication. But we are expecting to see that part 5 for the test and in a reverb chamber to be released hopefully in a matter of months. And again, this is just an example of the traditional layout for the test done at 10 meters or 3 meters from the device on the test in an anechoic chamber with a reflective ground plane. Now, an amendment that covered the electric vehicles, looked at what's called a REESS or charging mode setup, where you're still looking at emissions from the device under test during charging. The setup remains exactly the same, measurements done at 3 meters or 10 meters from the antenna with fixed antenna height, as is described in CISPA 12. And it allows for flexibility in the connection points of the charging harness. It gives guidance on the layout of the charging cable, positioning relative to the vehicle and the ground plane, just so that you have a good chance of repeatability of results. If you are in a position where there's not good control of setup functions within the test, then it means that repeatability is going to be very, very difficult. So all of this is really aimed at providing a standardized method of performing the measurements so that you have a good chance of getting repeatable results. And similarly for the traditional immunity type test setup, where you have your source antenna directed at the reference position of the vehicle under test. Again, if everybody does the test in a similar manner, then irrespective of who does the test, there's a good chance that you will get something close to what's expected based on the test setup. But obviously there are going to be cases where, again, common sense and good engineering judgment needs to be used to make sure that you're not inadvertently compromising the test. A good example is with a fan, for instance. If you're performing tests on a dyno and you have an air source that's predominantly large, reflective structure, then it could impact the behavior of your transmit source and compromise the results. If one person's doing a test with a large structure there and another person's not doing a test with that structure, then there's a chance you get different results. Just an example of some of the differences that you have to pay attention to when performing these types of measurements. So I think that was a fairly detailed overview of the traditional EMC type measurements. And as I said, I talked a little bit about some of the changes that have been introduced for the immunity and emission documents. What I want to talk about now is a little departure from the traditional EMC tests, but something that's still very important for the automotive manufacturers and the component suppliers. And this is really related to the increasing amount of communications that you have on board just about every vehicle platform out there, whether it's private cars or commercial vehicles. And to support that, a lot of this communications requires the use of transmitters, receivers, transmit antennas, and receiving antennas. And one of the challenges that manufacturers face is making sure that they can satisfy the RF needs of the communication link. And what I mean by that is the design of the radio, the transmit antenna, the over-the-air portion of the link, how much loss they expect to have over whatever minimum and maximum communication length they expect to see. And then on the other side, the receive antenna and the receiver, the receive radio that is going to interpret that received signal. That communication link has to be suitable for its intended function. So manufacturers have to come up with some way of demonstrating that, again, under controlled environments. And this is one of the areas where we're seeing increased interest in providing facilities to satisfy these tests. Now, V2X communication is just one aspect of the measurement. Another one is the use of advanced driver features, where those features, again, use some components that rely on over-the-air propagation. Radar is one of the examples that's used in quite a lot of the adaptive cruise control and autonomous braking and detection features. LiDAR is another one that's used, not necessarily what we would consider in the traditional sense of RF. And then cameras is another one of the sensors that's used. So what manufacturers have to try and understand is how best they can install these features on board the platforms in positions so that they are very effective in a cost-effective manner. And at the same time, the standards communities are trying to standardize on methods of sort of assessing and verifying the performance of these devices and standardizing the methods of communication, the protocols that are used and the standardized messaging systems that are used as part of the V2X and or V to everything related communications in the industry. So I'll talk a little bit about the antenna measurements and then talk a little bit about the ADAS side of the equation and how that plays into what we consider to be the traditional sort of RF environments. So one of the first things that changes is the frequency range. Before, we were concerned with everything from AM all the way through to televisions and satellite communication. I think was where we got up to the highest frequencies, and that included cell phones that were down in the 400, 600 megahertz band. Then obviously cellular bands frequencies started going up in frequency, where we got up to the LTE band. We got up to 5.9 gigs for Wi-Fi, DSRC, and up to 24, 26 gigs for 5G currently. So the frequency range is creeping up to higher levels for the different protocols that are used. And with the introduction of automotive radar, which started off in the 24 gig band, most manufacturers are now using the 79/81 gig band for a lot of the radar products that are implemented in the adaptive cruise control and sort of very many of the autonomous features. So what it means is that in our environments, we have to be in a position to support measurements under control conditions across this broad range of frequencies. And as you can imagine, in some cases, it's very challenging, and in others, it's very, very difficult. At the same time, we have to be able to do the traditional type of component level and full vehicle level measurements. So as an example, we looked at the traditional immunity test of a full vehicle with the antenna directed at the reference position of the vehicle. And you're driving and making sure that the wipers work, the lights work, the horn works, and making sure that the brakes work and nothing is interfered with by this incident RF energy. Now we have to perform that measurement with the addition of all these additional modules supporting completely different and in some cases very difficult to assess features like adaptive cruise control. If you set a vehicle to follow another vehicle at some speed and at some fixed distance, you want to make sure that that happens under the same immunity test conditions. So it really comes down to coming up with methods of bringing that into controlled test environments. On the antenna side, it's fairly well defined. There are a number of techniques that are available for performing antenna measurements on antennas that have different propagation characteristics. The full spherical measurement, it's something that's used for, very low gain antennas. If it's an antenna that's ground-based, you can do far field measurements at very great distances. If it's an antenna that's very high gain, you can do a full spherical measurement or a planar scan or a cylindrical scan. All of these techniques have been in the industry for decades and are very well understood. So what we're starting to see is the migration of some of these techniques into the automotive industry to help create test conditions for making measurements on these different antenna types with different sort of methods of integrating into the vehicle body. What you can see here is that there are a number of positions where antennas are placed. And in a lot of cases, it's a compromise of aesthetics and function. You want the antenna to work because you have to maintain the propagation characteristics, but you also want the vehicle to be attractive to users. You don't want large antennas sticking out all over the place. So it's often a challenge to try and sort of balance these two needs and do so adequately. So what we're looking at is, what we're seeing is more and more methods being introduced to help manufacturers perform pattern type measurements or radiated power and sensitivity type measurements on antennas that could be mounted on very different parts of a vehicle. And in some cases, antennas with very different propagation characteristics related to the functions that they are intended to perform. This is one example of upper hemispherical type scanning measurement setup, where you have the vehicle under test would be positioned and the antenna would scan over from the horizon over the top of the vehicle. This is a little model illustration of a vehicle under test sitting in a scanned bubble. as if it's sort of floating in space. It allows you to make a completely spherical measurement of the vehicle. And from that, you can calculate all sorts of antenna-based and propagation-based properties of that particular antenna. In the real world, obviously that's not practical. Cars drive on a road, so there's a ground, a floor. There's an area below which you're not going to have much in the way of antenna behavior. You're also going to have reflections from that surface. So you still want to come up with some method of either measuring or modeling the behavior of the antenna when it interacts with these boundary conditions that you have in a real world environment. This is just an example of a couple simulated patterns. And the intention here is to highlight one of the challenges that you have with making measurements on an antenna mounted on a vehicle. And that is the fact that the antenna is not an isolated component. It's not just an antenna that rests on the roof line or the wing mirror or the hood of the vehicle. In a lot of cases, it interacts with the vehicle body, and in some cases, the vehicle body is an important part of the antenna behavior. If it needs a ground plane, then the vehicle body provides that ground plane. So what that means is when you do an antenna measurement system design, you have to include the entire antenna within the measurement envelope that's used for that particular antenna. And in some cases, that envelope is the full vehicle. So it means that your antenna aperture is not just the 200 millimeters of the antenna element. It's quite often several meters in diameter of the vehicle body. So that increased aperture means that in some cases, it's just not possible to place the antenna in the middle of the scan range. So you have to come up with techniques that you can use to correct for that antenna offset from the center of the vehicle. So that's just one example of a couple of the challenges and compromises that you have to contend with in this type of environment. Another one is with the frequency range of coverage that's necessary. This is an example of a facility that's being used for antenna pattern type measurements at very low frequencies. As you can see, there's a reflective ground plane. In some cases, this ground plane is not just a metallic surface. It could be a partial absorber surface to create something that more closely replicates, the tarmac that the car will drive on. So you have a better indication of the sort of reflection characteristics of your antenna signal. The distance is obviously a function of the wavelength of the measurement. And with the limited ability to rotate the vehicle under test in more than one axis, this is quite useful for just doing single axis or single cut antenna pattern type measurements. Again, another one of the compromises where you're bringing techniques that are used for traditional antenna type measurements and trying to adapt those for cases where you have antennas mounted on different structures. This is an example of an implementation of, again, an upper hemispherical type measurement, where because of the short measurement distance, you're using near field scanning techniques and then using math to predict or calculate the far field pattern of the particular propagating antenna. Another example of, again, a combined approach where you're taking a traditional EMC 3-meter or 10-meter full vehicle chamber, very similar to the one we looked at earlier, but introducing antenna measurement arc so that you can perform some antenna measurements in this type of facility, again, with some level of compromise on overall performance. So if you look at the antenna measurement side of that setup, again, you have the scanning antenna arc with a fairly short measurement distance. You're still very much in the near field of very many of the antennas that are going to be used on board this vehicle platform. But you're still able to get, in some cases, quite accurate peak gain measurements or peak pattern measurements with this type of measurement setup. As is the case with the EMC standard, if you really want to get an accurate pattern, then it's always possible to improve the quality of the measurement with a more optimized design of the chamber. But what I'm showing here is really what we're seeing in the industry from customers that are trying to come up with methods of meeting a particular need, without having to go out and do ridiculous things to get quite acceptable results. And I think that's the true essence of engineering. It's you know, designing something that's just good enough, that just meets the requirements that of the particular test, and that's able to give you results that are very, very useful. A couple of the challenges, as I mentioned, one of them is making sure that you can move the vehicle around on the turntable surface to try and get the measurement antenna or the antenna under test centered as much as possible. Another one is trying to make sure that you can make measurements free from unwanted reflections. So in this example, it's possible to have absorbers on the turntable surface and on the floor of the chamber to try and reduce the reflections that you would have interfering with your measured, compromising the integrity of your measured pattern. And obviously, there's always the mechanical concerns to contend with, making sure that the vehicle is safe when elevated at some of these relatively high positions to get it away from the reflective ground plane. So we certainly started seeing interest in doing this type of measurement and installations in very many countries where customers are doing actually measurements on embedded antennas on different parts of the vehicle, just so that they can understand what these propagation characteristics are like, how the materials of the car body, the covering materials of the structure impact the performance of the antenna. And again, it's very similar when we start looking at the advanced driver systems. Again, there are many methods that are being used, some actual measurements, some simulated, some a combination of the two. And there are several companies that are in the business of providing a lot of these simulated environments. This is one example of a company that provides a video and radar target simulator. And the intent here is to really create an environment where you can simulate a target vehicle positioned in front of your vehicle's radar module. You can adjust the distance, the cross-sectional area of the target vehicle, and its speed, the Doppler of the vehicle, so that you have flexibility in where and how that target responds. You can also move the simulator, the RTS antenna, laterally to simulate lane changing and cut-in and cut-out scenarios. So there are a lot of things that you can sort of introduce to a controlled environment to try and provide us an ability to test some of these more advanced features on current vehicles in a controlled environment. This is another method that's used. It's the simulated environment. And these environments have a lot of representative small country lanes or highway sections with interchanges and on and off ramps. In a lot of cases with building and other structural obstructions, to try and replicate a true V2X environment so that you can demonstrate how a communication link would behave under different real-world scenarios. You can also do a lot of the tests on the adaptive cruise control, autonomous emergency braking, lane keeping assist, all under controlled representative environments. These are all steps that manufacturers have been taking to try and come up with methods of testing very many of these systems. And again, there's always a compromise. There's always something that's not quite a real world environment because there's something missing. And when you start thinking about bringing these things into an EMC chamber, it becomes even more difficult because you take it further and further away from a real world environment. So you try to replicate as much as possible of the needed stimulations that the vehicle needs so that it thinks it's on a real world condition while you're performing your emissions or immunity type measurements. Manufacturers have obviously progressed in the use of the sensors that are used for very many of these ADAS features. And whereas before a lot of the adaptive cruise control and emergency braking was related to the use of radar, most of them now use fused sensor systems where it relies on inputs from video cameras, either mono or binocular cameras, in addition to one or more radar sensors. And it compares the input from these multiple sensors to make sure that there's corroboration between what the sensors see before the vehicle takes the decision to perform an action. So simulating these environments becomes a lot more difficult. And again, we started seeing companies that are introducing sort of techniques where you can bypass the sensor and input signals directly into the associated module. So instead of having the camera look at a video image, you disconnect the camera and feed a video signal directly into the module so that you can create whatever video scenario you want artificially and input that to the module directly. And again, it's a compromise because you're taking it further away from the real world environment and you're removing the camera sensor itself. So if you have a camera that's immune to some RF environment, because you've bypassed the camera, that's a potential immunity that you're not going to be able to detect during the course of a measurement. So under ideal conditions, what you'd really like to do is immerse the vehicle under test in a real world environment that you can sort of bombard with all of the potential interfering sources and all of the vagaries and vulnerabilities of a real world environment and demonstrate that you can, perform reliably, continuously in those environments. But it's just not possible to do that. So we always end up with one compromise or another. So in terms of providing this sort of fused sensor system, this is something that a lot of companies have already started doing. A lot of the OEMs have started coming up with techniques based on a lot of these simulated scenarios where you can create a video stream either based on real video data or a simulated video image. You can create a radar stream based on simulated targets, either single target or multiple targets at different elevations or at different azimuth angles. And you can replay these scenarios to the vehicle under test in a controlled environment and try and replicate the ADAS functionality that you're trying to test. Several of the manufacturers, as I said, have setups based on video screens in front of the camera system, radar target simulators in front of the radar module, the vehicle driving on a chassis dynamometer, again, under controlled, predetermined driver scenarios. And then you would bombard that environment with the immunity environment. And again, make sure that if you tell the car to drive at 100 miles an hour and follow sort of 300 meters behind a very large bus, then you want to make sure that it'll continue doing that under all of the interfering conditions that you can throw at it. And those interfering conditions include the traditional immunity sources, the CW and the normal AM modulation, but also some of the other sort of interfering sources like, cell phone signals and other broadcast signals that are not necessarily all part of the current sort of immunity infrastructure that we play with. So just sort of some of the things that we've sort of been seeing in the industry, and I think introducing the antenna type measurement and the advanced driver feature type setups to the existing EMC environment is something that has a lot of motivation because there are cost advantages for doing that. You have an existing facility, you're adding to an existing facility, and you're potentially amending an existing standard. The trick is really making sure that what's done is sensible, pragmatic, and beneficial in providing useful data that increases the level of confidence that the device, meets a particular test requirement, and you can test it with enough vigor to do that. So I think I've bored you all to death. I'm not sure if anybody's even still connected, but in conclusion, test capability we've seen is been extended over the last few years and continues to be extending. There is proposals from different countries, different bodies to introduce some of these new test techniques to the sort of existing test scenarios that are being done. The intent is to obviously cover EMC predominantly, but it's really covering the traditional EMC tests with all of these additional ADAS related features and functionality. And that's what's driving a lot of these changes. And then making sure that as part of the V2X and the over-the-air communications, in addition to making sure that some of these other features are not interfering with V2X, it's making sure that V2X operates under the expected conditions. So the antenna measurements remains an important part of that. So from our perspective as a company that provides a lot of these test facilities, as a company that talks and meets with people across different industries, whether it be automotive, medical, aircraft and aviation, or the military. In most cases, it's always a case of coming up with an acceptable method economically that gives good coverage of the needed test type with acceptable results at the end of whatever is being designed and proposed for a particular measurement. Other methods like the reverb chamber is gaining popularity for obvious reasons. And as I said, it's been introduced for full vehicle testing in the automotive industry. And then we have the ADAS features, which I think would be among the discussions that we have within the standards community for some future revisions of the standards documents. And with that, I think I'd like to turn over to our chairman to either open the floor for questions or.
Thank you very much, Garth. Everyone, please feel free to open your microphones at this time, and please ask your questions to Garth.
I guess I'll break the ice here. That was an awesome presentation. I wasn't bored, so.
Well, that's good to hear.
So I'm kind of curious as to, the trends as far as like, some of the, like trying to do radiation pattern measurements on some of these antennas is not going to be practical. For instance, if all of a sudden the automotive world starts adopting like the 5G FR2 band, or even like the radar antennas, because those are usually like phased array antennas. So you're not going to be able to do gain, and they're at such high frequencies that really doing gain measurements is kind of impractical. And so what seems to be of more interest is like over the air type performance measurements. So now like if you have something that's you have a cell site simulator, like for example, for testing cellular performance, this would be at a vehicle level. You have a cell site simulator or something like that that's generating that's acting like a cell tower, and you put the appropriate antennas in the chamber, and then you would use that to do some sort of like vehicle level performance tests. These are some of the things I've heard about, but what kind of curious is have you seen interest from automotive customers or other on that kind of thing?
Yeah, that's a good question, and the answer to that is yes. At least the short answer is yes. So what you're describing is what we call OTA testing, over-the-air performance testing, and it's been used in the cellular industry for decades, where you're looking at the different elements of that communication link. So the transmit metric is the total power radiated from the device, and the receive metric is the total isotropic sensitivity. And the test is set up a communication link. You have a base station emulator. You initiate a call with the device on the test, and you tell the device on the test, broadcast at peak power, and you measure what its peak radiated power is. On the other side of the coin, you tell the device to reduce you tell the base station emulator, to reduce its transmit power, and you transmit a known data packet to the device on the test and say, well, did you receive the packet error-free? Drop the transmit level. Did you receive the packet error-free? And you create a map of the received signal as a function of orientation, sort of an antenna pattern of sensitivity of the device. And it's exactly the same thing that's needed in the automotive industry, where you have these V2X links. Ultimately, you want to make sure that when the car is communicating with a base station or roadside infrastructure, it can do that over some minimum distance, and you have to verify that it's going to work over that minimum distance very reliably. And then once you start exceeding that distance and you start getting call drops, you have to understand at what distance that happens and what the implications are for that to happen. So yes, we have certainly started seeing interest in doing that type of measurement. And it could be a very involved measurement, especially with relation to the orientation of the vehicle. When it comes to 5G and active patch antennas or directional antennas, that introduces a whole host of other measurement problems. And I mean, we've got presentations that we give on antenna measurements at FR2 frequencies, where at these frequencies, because the antennas and the devices are so much smaller, in a lot of cases you have no way of connecting to the antenna. So you're no longer able to do S21 antenna pattern measurement. You have to rely on over-the-air sort of communication link measurements. And if you have a very high gain array where you're steering the beam to improve the link in a particular direction, then the test setup has to be able to adapt to that. And again, there are methods that have been introduced to take advantage of the fact that these steerable antennas need to be told to point in a particular direction, and you make that measurement in that direction. And whether it's communicating in that direction or blocking communications in another direction is all part of a standardized series of tests that are being developed. So I guess the short answer to your question is yes, we've started seeing sort of interest in that. I think we're very early in the implementation of that type of test in the automotive community. The good news is not very many people are introducing high frequency or FR2 on vehicles. It's all very much LTE based, using the existing infrastructure. There was incentive to use the DSRC 5.9 gig band, but that got sort of usurped over the years by LTE and CV2X. So I think the good news is that it's using existing infrastructure, and there are existing techniques for doing it. So I expect we'll start seeing more and more of that being rolled out. But as I said, I think we're still very early on in the implementation of that test technique for the automotive community.
Yeah, thanks. That's kind of been my impression. The one difference between like what this what the cell phone manufacturers have had to do versus automotive is, you're right, they're doing those kind of TIS TRP type measurements, but they're kind of required to, because they have to get certified to by the carriers have requirements for the phones for that kind of performance.
That's right.
And if you don't, in theory, if you don't meet the performance level, they're not going to let the device on their network.
That's right.
Yeah. And the other thing, I mean, and in the automotive world, trying to do that kind of measurement, that's, the over-the-air type test, measurement schemes, are probably going to be needed, is not going to be cheap.
So there is one point that I think you're missing here, and that is understanding what the underlying requirement is. In the cell phone industry, a cell phone is designed to make calls and set up communication links. If it doesn't do that, then it's a piece of plastic. A car is designed to go from point A to point B. If it doesn't communicate over the air, it can still go from point A to point B. So I think the level of tolerance in the automotive industry might be a lot higher for poorer levels of performance in over-the-air links than is the case with the cell phone industry, where it's a mandatory sort of underlying requirement of the whole industry. So I don't think we'll see manufacturers saying, well, or anybody saying, well, you must be able to maintain a V2X link, with this particular performance criteria, or else you can't sell cars. It may mean that, that feature just may not be your best selling point. So there is that very fundamental and subtle difference between the two, which I think will remain very separate for the two industries.
Oh, I never thought about it that way, but you're right. This is, having radio communications on a vehicle is sort of like a ancillary. I mean, it could be considered important, but it's an ancillary feature. Its primary features, like you said, is to move somebody from point A to point B. Where with a phone, it's like if it can't connect to a radio, I mean, just like you said, it's maybe you can play games on it, but other than that, it's
It's a paperweight.
Yes, a paperweight. Yes.
Thank you. That's a very good question. Thanks for the question.
Okay, do we have another question? I'll ask one. On one of your slides, you showed 70 megahertz FM radio band. Do you have any further information on that?
So I just rounded the frequencies. I know the AM goes lower, and I think across the industry, there is an understanding. Understanding is the wrong word. I think there's a risk that AM will become less important for automotive manufacturers as a feature on board a vehicle. And there are a number of reasons for that. In Europe, for instance, I'm not sure there are very many manufacturers that still have AM radios on their vehicles. But I know things are a little different in the US in terms of the broad use of the AM band. But I think in the automotive industry, from what we're seeing from the manufacturers, we're not being asked to build facilities that allow them to do tests at AM bands. They're all concerned with, FM band and upwards, where they're looking at, key fob frequencies and the digital radio frequencies and satellite frequencies and cellular frequencies. Not very much interest in the AM band from the manufacturers.
Okay. I just wondered if there was something new I wasn't aware of there.
No.
Okay, any other questions for Garth?
I have another. Yeah, I talk a lot. One thing I noted, like when you brought up the frequency range for tests for CISPR 25, is that the current standards only go up to like 2,500 megahertz.
Mm-hmm.
And has there been any thought to extend that range? Because things I'm thinking of are like 5G FR1. You've got this new mid-band allocation from 3,300 to 4,200 megahertz, and then you've also got the extension of FR1, from 6 to 7.1 gigahertz.
So I think it's fair to say that there's work and actions on taking the frequency out to 5.9 or 6.1 gig, I think, somewhere around that band. But again, that's always been an ongoing topic. Where do you stop? Where do you cut off? And I think we're at that point where we're around about 6 gigahertz at the moment.
Yeah, I figured that the standards as they were, would make sense for the pre 5G world,
Mm-hmm.
because that's about where the cellular allocations or the use cellular bands kind of cut off. But of course things change all the time.
Well, before you create a limit, you have to understand what the threat is. And as Garth alludes to, if in the standards world, if you draw your paycheck from a laboratory, you of course want to extend the frequency as high up as humanly possible. If you're an OEM, you take a little bit different viewpoint. But regardless, the limits that are, whether it be CISPR 25 or CISPR 12, have to be based on some assessment of what you're trying to protect. And that is not an easy thing to come by.
No, of course, but that's the point, is like, vehicles are starting to become, equipped with cell modems that are supporting these, these new allocations in the 5G band. And therefore, some thought needs, because again, CISPR 25, the spirit of that is part of the spirit is protection of the radios on the vehicle from onboard emitter interferers. And that's why I thought about that. I'm like, I wonder if there's any thought of extending that.
That's true up to a point, but you also have to understand, how does the communication system work? I mean, I'll give you an example in the navigation bands, GPS L5 versus GLONASS. Well, they're both navigation, so I guess they must be the same limit. No, they're not.
Won't.
And that's because they don't operate the same way. So
Right,
just
but
in general, you just can't say, well, I'll just use the same limit I used for an analog
no, 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 no,
receiver.
I'm not.
It doesn't work that
I'm
way.
not arguing. I'm not arguing for a limit. As far as like I'm just arguing. The point I'm making is like is coverage for those other bands. Like right now, there's no consideration for anything like in from in the 3300 megahertz and up. Yet those are being used in the vehicle, and then there's so having at least some test coverage there or thoughts of test coverage there would at least be allow you to ascertain the what kind of potential problems you might have. Now, of course, yeah, setting the limits, you have to look at okay, where what's appropriate. It might be lower, or like in the case of GNSS, it needs to be very low because that's a very sensitive radio.
No, that's
Others,
not
maybe
true.
not so much.
L5 is far. No, it's because of the constellation. It works vastly different, and there's been a lot of research in that area. It's actually quite a bit more noise tolerant than say L5. So it's important. You could say, do you have services at higher and higher frequencies? But that doesn't necessarily mean you have to rush off and create requirements. At some point you do. I mean, as an example, if you talk about navigation bands, up until maybe 5-6 years ago, there were rarely any problems that would affect the navigation bands because your clock frequencies were so low that with any sort of good design practices you could manage that. But that's becoming more difficult as the clock frequencies go up, and with high-speed networks like FPD Link or GMSL for camera systems, now it is a big deal. So the environment certainly changes over time, for sure.
Well, I guess what'll probably drive that is they start seeing problems with with range and all that, and they determine that well, the radios are getting desensed by potential onboard interferers, but they may not.
Okay. All right, I'd like to move on with our drawing if we can. There's no other questions. So there's going to be 3 drawings right now. $25, $50, $75 Amazon gift cards. You must be present to win. The first random number tonight is 51. And 51 is Josephine Root. Josephine is still up online. Unmute if you are. Josephine,
I am
going
still
once?
online. I am still online.
Okay, excellent. So you have just won the $25 gift
Cool.
card from Amazon. I'll be
Cool.
sending you a email, or Amazon
Okay.
will actually. Congratulations.
Thank you.
Next number is 32. 32, Chris Lumen. Chris, you still here? Unmute. Chris Lumen, unmute if you're here. Let's have a look here. No. Okay. So we'll redraw for the $50. Number 55 is not here. At least Scott Diesel. I don't believe he was here. 41 is Joanna McClellan. Joanna, are you here? Didn't see Joanna. 26. Peter Hardinger. Peter. No. 72. Don Yorty. I don't think Don's here. It's taking a while today, sorry. 13. Louis Carrion. I don't have a check mark there. 52. is Gene Salzberg. Gene, you still here?
Yes, I am.
We have a winner.
All right. Gene Salzberg won $50. Congratulations, Gene.
Thank you.
The last one is for $75. Number 60, Candace Suriano. Candace, are you still here?
Yes.
Yep, I'm here.
Okay, congratulations, Candace.
Yay.
$75. Okay, I'm going to stop the recording at this time.